And any questions that you have as we go along, Ms. Narov will answer for you. Okay?
And I'm curious, does anybody here know what the PE stands for? Okay, I'll start by telling you what it is because I'm really not answering it in my presentation. Professional engineer. When you go to school to study engineering, you get a bachelor's degree or an advanced degree from school in the area that you're studying and specializing. But once you are out of school, first, while you're in school, you have to take a test that's called Fundamentals of Engineering. That tests your ability on everything that you studied about. And 5 years after you started working, you're entitled to sit for the second part of the test, which is now a professional exam that relates specific to the area that you chose to practice and addresses all the things that you will need to work with as you continue your career. And if you pass that test, you become a licensed engineer or a professional engineer, and you're entitled to sign drawings that relate to the discipline that you're working. So in order to be able to really work, you need at some point to get a professional engineering license, and it's granted by the New York State Department of Education. You are lucky in the sense that you're in the School of Architecture and Design and you're in Williamsburg right now, and as you see what's going on around you, I must have at least 6 or 7 projects in the area that I'm working on or just recently finished. So there is a lot to see in terms of the actual application of what you're studying here. So just when you walk around, open your eyes and ask questions because you can learn a lot by just being in this environment these days. So what type of structures are there, right? There are many things. If you want to look around the room, there are so many things that are structures that you don't even think about the structures. The table that you're just now leaning your elbow on has to be strong enough to sustain the pressure that you're putting on it, right? It's a structure. The chair that you're sitting on is also a structure. I don't design chairs, I don't design tables, I design somewhat bigger things. So the type of structures that engineers are involved with start with buildings. We essentially make a building stand. That's my job, is to make sure that it stands. I'll get into more detail as I talk. Bridges are structures. Art installations. If you look at the spider that was conceived by an artist, an engineer had to make it strong enough so that it stands and doesn't get blown over, right? And many other things are structures. Airplanes are structures. Cars are structures, right? There has to be a component that involves a structural engineer. There are other disciplines involved, but it has to be at least one structural engineer involved. I'm going to talk here today because this is the area that I specialize in. So there are different types of buildings, and the type of building affects the design of the structure for the building. It affects the place that you put columns in, it affects the place that you put walls in, it affects the material you select to build the building from. So what are the different types of, we'll call them occupancies of buildings that we design to? The most common ones are listed here. You know, when you look in Manhattan or around you in Williamsburg, most of the buildings are built for people to live in, right? Those are called residential structures. Hotels are a sub-area of residential structures because essentially people live in hotels too, granted for 1 night at a time or 2 nights or a week, but they're still functioning as residential structures. There are buildings that house both. They are called mixed-use facilities. They are industrial facilities. When you build a factory, when you build a hangar, the whole set of rules that you use to design them is different. For example, if you build a factory, you need to have a very large open space. There's no reason when you do a school to have a space that's bigger than this classroom, or maybe you have an auditorium in here or something that's slightly larger, but the whole approach is different. So you don't want to build a huge space if you're not going to be using it as a huge open space. So you can place more columns and you can save money on the construction of the facility. So that's why it's important to understand what a building is going to be servicing to design the building. And of course, we have schools, we have museums, we have airports. Can you think of any other type of structure? I mean, there's, very many occupancies in different structures. So when we build up, we call it vertical construction, right? We build high, we build 1 story or 2 stories or 50 stories. It's all called vertical construction. When you build to cross over something, it's called horizontal construction. And what do we build to cross? Anybody ever see at Kennedy the airplanes taxi over the highway? Did anybody ever notice it? You need to build a bridge that's strong enough to hold the weight of that airplane. Bridges can be over water, right? There can be over a ravine or a dip, or between 2 mountains, between 2 high points. So they are over topographical obstruction. And sometimes you need to cross over a highway without having a traffic light, right? So you build over the highway. So one car can go this way and the other car can go this way. That's a bridge. I put this slide up of somebody being very creative and designing a bridge that both looks amazing and serves its function. So let's start with buildings. Again, I said I'll be concentrating today on buildings and on bridges, because those are the areas that I practiced in. So buildings. Who has to be involved in the design of the building? The first is architecture. That's the first discipline that's used, that needs to be mobilized to design a building. And it's actually the first discipline that gets involved, because an architect comes in to first find out what you can build on a site. It's called zoning. There are rules and regulations about every site in the city, what you can build. Can you build a commercial space? Can you build a residential space? How many square feet? What the area of the building that you can build? So the architect gets involved and helps the developer decide what the land of the piece of land that he just acquired is good for. So architecture is involved in building design. Structural engineering is the next discipline that comes in, but actually the first that gets implemented. Because before you could do anything with the building, you have to have the structure in place, right? You can't finish it, you can do mechanical system, you can do anything until it's built. So that's the next discipline. And then there's the mechanical engineering, electrical engineering, plumbing engineering, and many more. These are the major disciplines, but there are many more. And as we develop more and more sophisticated buildings, you need people who specialize in lighting and in what we call low voltage. In other words, providing enough cabling for internet and computer access and security systems. So there's many more smaller disciplines that come in as the building gets developed. But these are the major disciplines from the day that the building became a smart building, so to speak. So for architecture, I told you that the architect helps, define what the site is good for, but the architect also has to lay out a program for the site. Because the owner has to tell him what he's trying to build. The owner has to make money on the site, right? So he needs to have an idea of what he wants the building to be used for. At this point in Williamsburg, if you're going to come in and build, let's say, a factory, it won't be the best use of the space, because you won't be able to get enough income to justify the cost of building it. So in Williamsburg, most of the occupancies that we see nowadays are residential and hotels. And now there is a beginning of some office space, because some of the high-tech companies like to be here, because the young people who rent apartments here would like to work near home. So we are starting to see some offices coming. So the architect has to work with the developer to come up with the program and develop the layout of the space. For example, if you have a school, right? You need to have classrooms, you need to have an auditorium, you need to have a lunchroom, you need to have bathrooms, right? You need to locate those, all of these on a piece of paper so that you know where everything is and that you have enough room to do everything that you need to do. Then the architect does the aesthetics. You know, what is the building going to be looking like? How is it going to be massed? I understand that you're doing massing studies or starting to do massing studies. The architect is the one who is determined how the building is massed. And it's not just for aesthetics, but also for regulation. The city ascribes to every building how tall it can be, how wide it can be, how it needs to be set back from the streets, etc. The architect also has to make sure that you can come into the building and get out of it. And when I say this, the get out of it sometimes is in the case of emergency, so there has to be enough exit points in the building. The architect picks materials and finishes, and a lot more less pronounced disciplines. The structural engineer comes in and does the foundation design. What is the building going to be sitting on? Sometimes it's in a site that you can put just pour concrete into the ground and put a column on it. And sometimes, a lot of times in Williamsburg, you have to drill piles. Have you heard the noise that comes with pile drilling around here? That's very noisy, but the reason you do it is because you cannot find good soil underneath the building, so you need to go deeper to find a good support for the building. And then the engineer does the superstructure design, which is make the building stand, as I say. So what I have here is a few slides. One showing, this is the almost finished, not quite finished, but already starting to shape up the architectural finishes. But what it started out is in a big hall with reinforcement, then concrete was placed, and then stairs were placed with temporary railings, which will then be replaced by much nicer railings. And here is when the architectural finishes start to come in. So you see some progress. The use of electricity in building almost tripled from the time that I started working, because of the fact that we have so many more things that we plug in now than we ever had before. And the plumbing engineer does the piping for everything that needs to be piped. Water, hot water, cold water, gas, sewer, everything that needs to be in pipes, the plumbing engineer is responsible for. I have an image here of the Freedom Tower as it was going up. It's hard for me to find pictures of actual mechanical equipment because usually by that point I don't go to the project, I'm done already. So I just showed you a building that's shaping up. What is this like? Think about the human body, right? I'm, as a structural engineer, responsible to build your skeleton. That's what keeps you up, right? That keeps your hand, gives the hand the strength to do things. The plumbing engineer does the blood vessels and all the other liquids that roam around your body. That's his responsibility, right? The mechanical engineer is the organs. The electrical engineer is your nervous system. And the architecture comes and dresses you and shapes you and puts the flesh and skin on your body. And that is the mechanical engineering. I know what I hear over the years. I've been designing buildings in New York for over 40 years. So something rubs on after so many years. But I know very little about all of these other systems. Same thing with architects. Architects need to have, we are called consultants. They need to come to us to help them put the building together. They cannot do it by themselves. Buildings were a lot simpler, a lot less complicated. And the architect was it. He did everything. He made the building stand, he made the program, he made the appearance, he made everything. There was no electricity, there were no mechanical systems, so there were less specialties that were required. So one person could master the whole knowledge that went into putting a building together. It's no longer true today, and it's getting more and more complicated as time goes by. So there are many opportunities, by the way, to learn skills that help in the design of buildings and bridges. Bridges are a little simpler. Does anybody know what a civil engineer does? Okay, for example, designing alignments on a highway. That's a civil engineer. Designing the grading of a site, that's a civil engineer. So civil engineer is mostly with land, deals with land and, a land level specialties. Hydraulic engineering comes out of civil engineering. Geotechnical engineering, anybody knows what geotechnical engineering is? That's foundation engineering, in another word. That's the geotechnical engineer is responsible for examining the soil. Before you start a building, somebody has to drill into the ground to tell you what's in the ground. Is there water there that you have to deal with? Is the soil able to support the building, etc.? That's a geotechnical engineer. And these are essentially the biggest discipline of civil engineering, and all of these get mobilized in the design of bridges. Having said that, if you see the difference between a bridge that looks very structural, it was probably designed without an architect. But if you see a bridge like the one on there, or the one I showed you on the slide before with the red arches going into each other, that usually had an architect involved, because architects are trained more aesthetically, and sometimes you need, even for a bridge, which theoretically all you need is engineering for, having an architect involved will improve the appearance of the structure. Having said that, what we call, in a sense of bridge, the involvement of the architect is the architect brings a quality that cannot be assessed economically or cannot be assessed in terms of the value to the project. But when you build a bridge that looks better, the whole environment is more inviting, right? When you're in a nice environment, you want to be there. When you're in a not so nice environment, you can't wait to get out of it. So the architect, even in the design of bridges, can bring some value to the design. Okay, so I started telling you what a structural engineer does. I'd like to elaborate on it a little bit. The first responsibility I have is what we call to ensure structural integrity. For years, I had trouble explaining to somebody what I do. I said, I'm a structural engineer. I design buildings. So are you an architect? I said, no, I'm not an architect. I'm a structural engineer. You're way too young to remember this, but there was a big collapse in a Hyatt hotel in Kansas City. A big walkway came down with significant casualties. And only after this did people around me, close to me, understand what I'm doing. Because if I'm doing my job right, things like this don't happen. So that's my number one responsibility, is whatever I do, the building has to stand up. This ceiling cannot come down over your head, even if there were people dancing on top of you, right? So that's my number one job. The second job is to identify all the loads that the building is going to be subjected to during its life. Can you think of some loads? Up there. You come into the building, are you a load? Are you weight that added to the floor? I have to make sure that you are safe and sound, and that coming into the room, even if it's filled wall to wall with people, the slab is not going to come down. During a hurricane, what happens during a hurricane? Wind do what to a building? They push it, right? That's a load. Earthquakes in places where did you guys recently hear about the earthquake in Taiwan?
Yeah.
buildings came down because they were not properly designed for the load that the earthquake imposed on them. Flooding. Remember Hurricane Sandy? How much damage was caused by flooding? Go ahead.
Well, actually, isn't there another job for civil engineers to also kind of prevent global warming, such as floods and hurricanes and tornadoes, from tearing down a building? Isn't that kind of like another job for them to kind of come up with a structure that's able to maintain its balance?
To the extent that global warming affects building, the answer is yes. But we don't get involved in actually studying global warming. But if global warming is going to cause water to come in and undermine the foundation, that needs to be considered in the design of the building, yes. And on top of it, nobody wants to build an expensive building. So we have to find all of these solutions in the most economic way that we can. So of course you can build bunkers and they'll hold all the loads that you want. But that is not going to be affordable to build. So we also, engineers, have to consider the cost of construction. So when I explain the discipline of engineering, the best way to explain it is we use physics, we use math, and we use chemistry. But those are sciences. They are not applied areas of study. They are theoretical sciences. The engineer takes the knowledge in physics, math, and chemistry and adds an economic value to use materials and to use elements of construction in the best economic way. So it becomes, and that's true, by the way, for the transition from science to engineering is the addition of the economy of what you're doing. You can build amazing stuff using electrical engineering, but if you cannot do it in a way that one can sell a product, then you have not accomplished anything, because nobody is going to buy your invention. So you have to marry the knowledge from the area of the pure science with the application and the economics of the work that you're doing. And as science developed, more and more materials were developed. It was about the end of the 19th century and the beginning of the 20th century that materials became so developed that they allowed us much more freedom in the design of structures. For example, concrete. Concrete in different forms. You know what concrete is, right? It's the mix of cement and sand and stone and water to give you an artificial stone. The knowledge to make some form of concrete existed before. But concrete is only good when you push on it, what we call compression. If you pull on it, it falls apart. So in the late 19th century, somebody came up with the idea, maybe if I could put a bar of steel in the concrete when it wants to pull apart, it's going to hold the concrete, and the concrete combined with, what do you see out there when you build buildings from concrete? You see rebars, reinforcement bars, you see steel bars sticking out of construction. The combination of concrete and steel is a lot better than concrete alone. Natural quality to get this. You couldn't really do it in steel. Now, having said that, this building was opened in 1973. The computer technology that was available to us then was much less advanced than what you guys are familiar with now. And it took many more hours of design to even map the geometry of these buildings. Today, it would be a cinch with computers. And then there were computers, but they were so behind what you are used to now that it took many, many people hours to get this building, even just the geometry defined, let alone the design. This is the Boston City Hall. It's another building that was built in concrete. And we call this exposed concrete. You know, when you see the concrete in the final product, you don't put glass or you don't put other materials on it, stone, that's called exposed concrete. That's also a quality that concrete has. It's very difficult to expose steel in a building. You know, you see towers that transmit cell phone signals, right? Those are exposed steel because they are looking in all kinds of places, in the woods somewhere upstate. And who doesn't know where the Chrysler building is? Definitely need a trip to Manhattan, School of Architecture and Design. It's right by Grand Central, not far. And this is the very shiny steeple of the building. And this is the structure that was put behind to prepare it for the finishes. So all of this is not visible now. But that's what was put in place to build the Chrysler building. You are familiar with the Empire State Building, right? That's the first skyscraper that was built in New York. That used to be the tallest building in New York for many, many years, but no longer. And then there are more modern materials, you know, plastics. We call them composite materials, very unusual metals. How am I doing on time?
About 7 minutes.
Okay, I'm going to rush it now. Okay, we have all kinds of very advanced materials that make our design a lot more sophisticated. Okay, I'll go through this very quickly. I want to show you some bridges. I think it's always very interesting to see. This is a natural bridge. Who made this bridge? Which engineer designed it?
Earth, Mother Nature.
Mother Nature designed it. What happened is it got washed out and you ended up with a bridge. So that's a bridge, a simple bridge. The ancient Romans, you see, built a lot of viaducts and bridges, but they were always very short spans and very heavy, right? Then, even in the 19th century, this is a masonry arch bridge in Scotland. It's used as a rail bridge. Even in the 19th century, the knowledge and the materials that were available still didn't allow them to do what you will see in a minute. They were still building very short span and very heavy structures. You see how heavy it is? Big columns, big beams, big everything. But arch is a very clever way of doing it, using an arch. And we don't, is a steel bridge. Do you see what happens to the span? Did it get bigger? Much bigger, right, than the arch before? You look at how much less material was used to create the same structure, right? So it spans longer and you need less material. This is a modern multiple steel arches. Look how much less material is used here. This is in China. This was completed recently, 4 years ago. You see the elegance with which the materials are starting to be used, right? Am I impressing anybody? I guess not. What is this? Does anybody know this? The Golden Gate Bridge. Do you know which one was the first suspension bridge that was built?
This one?
No? No? The Brooklyn Bridge. You can say it loud if you know. Yeah, the Brooklyn Bridge. Now, it's a lot heavier than this, obviously, but it was the first suspension bridge. In New York, we have a lot of suspension bridges. The Triborough Bridge is a suspension bridge. The GW is the Verrazano Narrows for a while was the longest suspension bridge. It's been overpassed. The Whitestone Bridge, I said Triborough or RFK Bridge, and the Clearview are some of the suspension bridges in and around New York City. This is a cantilevered bridge. These bridges are built around a major center core, and then two arms get sent out. And then another piece is built the same way, and then you connect the two. And what holds it together is the two arms that are extended like this. So it's called the cantilevered bridge. Again, very little material, very much larger span. This is also very recent, was opened in 2014. It's in Greece. It's connecting two sides of the Corinthian Straits. On one side there is a city called Ryan, and on the other side there's a city called Anti-Ryan. And look how elegant this is. This is called a cable-stayed bridge. When you look at the suspension bridge, you see that there are two towers, and then the cable drapes between them, right? When you look at the cable stay bridge, you still have towers, but what happens to the cables now? They're straight. You see that they're straight? So the column actually holds the cables down. With the draping, the column loads, the tower loads are not so great. With this, the column is the anchor. And you see that the cables are straight, right? They're not draped. There are cables coming out of this tower, and then cables are coming out of the other tower. So it's slightly different approach, but it's still cable, the cable bridge. And there are heavy concrete segmental bridges. The beauty of these is, what is, in your mind, why is it difficult to build a bridge?
That's the structures to be heavy. Because the materials can be heavy.
Okay. All right. When you build a building, what do?
You plan out a blueprint.
You start from the ground and you build it up, right? Like blocks. What do you have to do when you build a bridge?
You have to make foundations. So it stays.
But you have to go over what? Over water.
Yeah.
It's not so easy to build a bridge, right? So the biggest problem in bridges is actually building them. You need a bridge to overcome an obstruction, right? How do you overcome the obstruction in building the thing? So this is one of the methods where you see the equipment, it keeps pushing out and tightening and pushing out until you have the full bridge with all the pieces. Anybody, does this look familiar to anybody? Reminds you of a structure in New York City?
And that looks like the BQE.
This? No?
Right there.
No, I'm talking about the pieces. Anybody ever goes to Kennedy Airport?
It's an air train.
Thank you. The air train was built using segmental construction, right? And here are some crazy bridges. You see the Tower of London? Tower of London is what we call a movable bridge. Why do you think they needed to move?
For big boats.
To allow boats, right. The road is at one elevation, you need to cross the water, but it's not tall enough for the boats to pass through, so you build a mechanism that allows the bridge to go up and down. And look at these crazy ideas.
That's in London.
That's in London, right. I don't know where these are. These are just pictures I found. This is a viaduct in France that was very difficult to build. It goes for quite a distance. And the reason it was there is no water. There's no water to pass, but you went it's in the Alps, from a very tall place. You had to somehow get people down to a populated place. Anybody recognizes that one? Thank you.
Oh no, so that's not water?
What? This is no water. No, there's no water. It's a big drop in altitude.
Oh.
Anybody recognizes this? Anybody's been to the downtown Manhattan? Thank you. This is the new PAD station. I picked 3 projects. Anybody heard the name Santiago Calatrava? He happens to be an architect who also has a degree in engineering. So his structures tend to marry both appearance and logical engineering. So this is a museum in Milwaukee. I'm not sure where this is, but this is a walkway. This is a reflection of the structure, and this is what is going to be the new PAD station downtown. Do you recognize this building there? That's a residential tower also in Manhattan. We're lucky when we live in a place that what you study about architecture here, you could go out and see, right? So New York is a great place to be for this. But this is the California. These 2 projects are in Los Angeles, and this is a project in Ohio. But this architect is known for taking all the normal shapes that we're used to and twisting them and turning them. And what makes it possible for me to design is the advanced computer technology. And I thought you enjoyed this. This is in Vietnam. It's a recently completed bridge. What does it look like? A dragon, right. So again, in all likelihood, there was architecture involved in the design of this structure, although it's a bridge. How am I doing?
Great. Here's going to end in minutes. Anybody have any questions?
I was good in math and physics. I like the combination of architecture
Hold on a
and
second.
engineering.
Wait.
I was lucky, I chose it at a very young age, and I still love what I do. If I didn't convey that, then I didn't do it.
Thank you. Let's have a big thank you, everybody.
Thank you.